So we're going to come to the heart of this chapter, which is simple harmonic motion. Essentially, simple harmonic motion is any motion that follows Hooke's law. Okay, so Hooke's law is completely crucial to simple harmonic motion. One of the examples of simple harmonic motion would be the spring mass system, either horizontally on a frictionless surface or vertically, since it then follows Hooke's law and hence demonstrates simple harmonic motion. Okay, so the main thing about Hooke's law is that the force is proportional to the displacement and always in the opposite direction. Okay, so F is proportional to negative x, or F is always directed towards the equilibrium. Okay, another example of the spring mass of the simple harmonic motion would be the pendulum, with the caveat that it's only true for low angles, and we'll come to the pendulum in a minute. Okay. So in general, the simple harmonic motion will produce over time a wave-like motion going out. And this is a wave which is going to introduce you to a few concepts about the wave. We already looked at amplitude, which is the maximum displacement from the equilibrium line. The part of the wave which is upwards is called the peak or the crest. Okay, two words, crest or peak. And the lower part is called the trough. The peak and one trough together make up one wavelength, okay? But it doesn't have to start from the beginning here to the ending there, which is shaded. You could go from the top of one peak to the top of the next peak, and that would also be one wavelength. It just means you start from a point and you go to another point which is exactly in phase with it. And I'll explain later on what in phase means, okay? But you're taking one pattern, one entire unit, which will then repeat. So that entire pattern, the up and down, starts repeating here, up and down, and further up and down, and so on. So this one entire pattern is one wavelength, okay? If you plot time on this axis, okay, then the time taken for one wavelength to travel through is called one time period, or uppercase T, and the frequency is the number of such waves that fit in 1 second. So frequency is 1 over time period, okay? Now, we can apply Newton's law to Hooke's force as well, okay? So Hooke's force is F equals negative kx, and F is also equal to m into a from Newton's second law. This means my acceleration A equals negative kx divided by n. Yeah? So where x is displacement, m is the mass attached to the spring. Okay. But we know that A is now dependent on x, so it's not constant with position. Hence, we cannot apply kinematic equations, okay, which had to be under uniform acceleration. Okay, so we looked at the three equations before for displacement, velocity, and acceleration. Okay, we're going to consider how the simple harmonic motion is related to uniform circular motion. So for this, I want you to consider a point P, which is moving in this uniform vertical circle. What does uniform mean? It means it's keeping a constant speed as it goes around the circle. Okay. Obviously, its velocity is changing because the direction is changing, but the magnitude of the velocity is staying constant. Okay. From above, we're going to shine a light and we're going to look at a table or a piece of paper below to find where the shadow of this dot is. Okay. So if the dot is at P, its shadow is going to fall directly beneath it at this extreme. As the dot rotates from P to Q, it's going to be in line with the center, and its shadow is going to be right here in the middle, yeah, in the middle of the dashed line. As it travels further to, say, P prime on the opposite side, its shadow is going to fall here in a straight line down, yeah, to the other extreme. And then it comes down to, let's say, Q prime, again in line with this, and it's back at equilibrium. And then it goes back to P, it comes back here again. So while P has executed a circle, a uniform circular motion, its shadow here has gone on a straight line from one extreme through equilibrium to the other extreme, back to equilibrium, back to this side. And what is this kind of motion called? We've seen it before. We've seen it with the spring mass system. This is our simple harmonic motion. Okay, so a shadow is performing simple harmonic motion. So there's a relationship between circular motion and simple harmonic motion. Yeah? And here it is. Here the red dot is my point P, and as it moves around, you can see that the blue dot, which is a shadow, just goes on that straight line and executes simple harmonic motion. Okay. The period of that motion, which means you start at one end, you go through equilibrium to the other side, back through equilibrium, back to original starting point. So one complete oscillation. The time to do that is called the time period, and it's given by T equals 2 pi under root m over k for a spring mass system, where k is the spring constant, m is the mass. Yeah? And since f is 1 over t, the frequency is 1 over 2 pi under root k over m. Yeah? The units for frequency are per second, which is given a new name, which is called hertz. Number of cycles per second is hertz. Okay. So again, what is one cycle? One cycle is you start from a given point, let's say the lowest point here. We go through equilibrium to the highest point. We come back through equilibrium, back to the lowest point. So that entire journey up and down makes one oscillation. The time for that is one time period. How many such oscillations you fit in to 1 second tells you the frequency. Okay? Okay. So that frequency f is related to the angular frequency omega through the 2 pi radians. Okay, so 2 pi f is the same as omega. Okay, and if you take the formula for f, the 2 pi and the 2 pi are going to cancel and leave us with omega equals k over m. So the angular frequency, omega is sometimes called the angular frequency, gives the number of radians per second, and the frequency gives the number of cycles per second. Okay? If you actually perform this experiment in the lab, which you will, and you'll measure the time period of a spring mass system, okay, or a pendulum system, and you plot t squared versus n, then you might find that it doesn't actually go through the origin, which is what you would expect because it has no constant term. So it should go through the origin. But in reality, the spring does have a finite mass, and hence it doesn't go through that point. Okay. So here is that reference circle again. We call it the unit circle. Okay. Here's my point P on it. Here's Q, which was the shadow before. And if P starts here, then P and Q are coincident. They are both at this point. As P goes up, Q starts moving to the left until P comes up here, it's traveled 90 degrees, and Q comes at the origin at equilibrium. Once P comes all the way around this side, it's again coincident with Q, and so on. Okay? So we can see clearly here that if the radius here is written as A, uppercase A, then the distance x that Q is away from the origin is given by A cosine theta. When Q is at the origin, it's 0. Yeah? So it's at equilibrium. When it's at the extremity, it is exactly A, where cosine of 0 is 1. So we see that this position x is given as A cosine of the angle theta, where that angle theta is the same as omega t. Okay? Where omega is the angular frequency or angular velocity. Okay? So omega is same as 2 pi f. And we saw these graphs before. Yeah? This is my position time graph, just repeated here. Yeah? This is the velocity time graph. Remember, the negative omega A sine omega t, and then we're going to get another cosine, which is an opposite of this, but not equal in magnitude, because in magnitude, we have the omega squared term multiplied into the A now. So this is no longer A, this is omega squared A. Yeah? Okay. Here are our formulae. X equals A cosine omega t, B equals negative omega A sine omega t, A equals negative A omega squared cosine omega t, and the ones to the left are just replace omega with 2 pi f, right? Okay, so let's do a simple problem on this. A 4 kg mass is attached to a spring and is observed to oscillate with a time period of 2 seconds. So let's say T1 is equal to 2 seconds. And this is equal to, I've given you the formula here, which you would have to bring to the problem. It will not be given to you. 2 pi under root m over k. Okay. And let's replace the n with 4 kgs, right? So let me replace that n with 4 kgs. So long as we're in the MKS unit, you can just put in the numbers. What is the period of oscillation if a 6 kg mass is attached to the spring? So I want the case for a 6 kg mass. So I'm going to do the time period for 6 kgs. This is what I'm looking for. I'm just going to call it T. And it's going to be given by 2 pi under root 6 over k. Since it's the same spring, it's the same k. And I'm going to divide this equation 1 by equation 2. Yeah? So I get T over 2 on the left-hand side equals root 6 divided by root 4. Yeah? And then you just need to solve for this and see what you get. You should get the same as me, which is 2.45 seconds.